This is a classic problem to find the volume of a cone of radius r and height h. I'm going to show two methods for how to do it. One where we don't use a coordinate system and one where we do. So first the non-coordinate system, where you just draw a picture of a cone, radius r, height h, and I decided to mark it off little h going from 0 to capital H, but you could do that in the reverse. And here's the capital R. Then we take a representative slice, which is represented by the green slice, and that's radius little r, out at a height h from 0 to, so I'm saying from 0 going this way to right here, that's the h. Okay, so very similar to the optimization problems that we had. This length here is capital H minus h, so we set up a ratio of little r is to capital H minus h as the big radius is to the big height, because you have this similar triangle set up here. Here's the big triangle, and then you have the small triangle inside. Okay, so then that produces this equation, solving for little r, because we're going to write everything in terms of little h as it moves from 0 to capital H. So the volume of this slice is, it's a little cylinder. The slice is a cylinder. It's pi r squared delta h, because the delta h is the height of the cylinder there. This is a cylinder. Alright, so then when we plug in what r is, that's this quantity, we get the expression for the volume of the slice out at a value of h. So the volume of the cone is approximately going to be the sum, as you add up all those slices from h going from 0 to capital H. So that's this. Then you convert that into an integral as the number of slices goes to infinity, and in other words that the delta h goes down to 0, and that produces this volume of the cone. Then you use the algebra trick of factoring out all the constants. Constants factor out, just leaves you with this expression in here. And then I'm using another algebra trick of the trade. Capital H minus little h squared is the same as little h minus capital H squared. All I'm doing is turning around the subtraction, and I'm able to do that because I have a square, and it's going to come out the same. But I could have still done it without doing that. Then, using a little calculus trick, instead of doing u substitution on this, which we certainly could do, could have done u equals little h minus capital H. And instead of doing that, I realized that if I had this u is equal to h minus h, du would have been dh. So, in other words, I can just go ahead and integrate up h minus capital H cubed over 3, and it's going to be okay, because if I differentiate that, I will get returned back to the original statement. So it's a little bit easier. I could have squared out that integrand there, of course, and done it term by term. That's another way to have done it. And that's running from 0 to h. So I just plug in the algebra using the fundamental theorem of calculus and work it all out, and it comes out indeed to be the volume of the cone formula, 1/3 pi r squared h. Another way to do this problem is to set up a coordinate system, and it comes out a little bit easier. Here, take the cone and put a coordinate system on it with the x and the y, and you can see the slanted side. Then find the equation of that line, which is just capital R over h is the rise over the run to get to this point. It starts at 0, 0. So it's y equals capital R over h x. Then come over to this picture, draw your slice. It has a little r radius, and it has a delta x height there as far as the height of the cylinder, which is what this is. Okay. Well, the radius is the y height at a given h value. So in this case we're calling it x. At a given x value, the height is the y value there, x comma y. So we say, alright, the volume of the slice is equal to pi r squared delta x, but the r is the y value. The r is y, and that happens to be r over h x. So plug that in and square it, delta x. That's the volume of the slice. So then, just to jump right into the integral, the volume of the cone is going to be this expression, 0 to h of that integrand. Again, factor out all the constants, and you just have an x squared left in there, which integrates to x to the third over 3, evaluated at 0 to h. Plug it in, do the algebra, and you get the same cone formula.